So in the last video we looked at just one part of Theorem 29, but there's a bunch here. And this is, all of this you might call set algebra. Algebra in the sense that intersection and union sort of act like, I mean, they are binary operators, kind of like addition and multiplication would be for numbers. And so you can think of all these as kind of like algebraic properties. So like plus, intersect is also commutative. This is a property that plus also has, right? And times for numbers. Associativity. Distributivity is kind of an interesting one and worth paying attention to for a moment. So if you have something unioning in against an intersection, then it distributes. The union distributes. So it's as though here, it's as though this is times and this is plus, right? So A times B plus C is A times B plus A times C. But interestingly, intersection also distributes over union. So here, in this part of Theorem 29, the intersection is now behaving like the times and the union is behaving like the plus. So that's kind of neat. Another interesting one is how the empty set behaves. So if you union something with the empty set, then you get the same something back. That's kind of like what happens when you add 0 or when you multiply by 1. So the empty set acts like a 0 or like a 1, depending on whether you're unioning or intersecting and whether you want to think of that as times or plus. Okay, so that's all I'm going to say about Theorem 29. And now I want to look at 30 and 31, which give you a nice way of thinking about what intersection and union do. An alternative way of thinking about, rather than just, with two bags, what happens. It helps you to think about the intersection of two sets, B and C, as a particular kind of universal object. So by that I mean, think of it in terms of the properties that it has rather than in terms of what it is. So what properties does it have that make it unique? So the intersection of B and C is going to be, first of all, a subset of B and a subset of C. So that's one thing that it achieves. It is a subset of B and it is a subset of C. But that's not enough to make it unique, to pin it down. In addition to being a subset of B and a subset of C, it's maximal. So it is, in some sense, the largest thing that has those properties. It is a subset of B and it is a subset of C, and it's the largest such thing. If you think about collecting together all the subsets of B and the subsets of, if you think about collecting together all things that have this property that they are both a subset of B and a subset of C, then the largest among those things is what the intersection is. So these items here, 1, 2, and 3, that's what they're trying to say. The intersection is a subset of B, it is a subset of C, and number 3 is the way of saying it's the largest. Largest means if you have any other such thing, if you have any other guy A here, who is also both a subset of B and a subset of C, then B intersect C is the largest in that it contains this other one. So it contains anyone. So B intersect C satisfies properties 1 and 2, and it contains anybody else who also tries to satisfy properties 1 and 2. Okay, let's prove Theorem 30 together here. And I know you can just read about it, and if that works for you, go ahead and do that. You can skip the rest of this video. I'm just going to do a video version of it here, but I think I can add some commentary that might help for some things. So the goal is to prove that, well, it looks like I miswrote it, so that's my first mistake. It's B intersect C subset of B. Okay, so I sectioned off this kind of scratchwork area my goal is to prove that this inclusion statement, right, that contains a universal quantifier. So my goal is to prove, I'm just using the definition of inclusion, that everything that's in B intersect C is in B. That's the goal. So there's only one way to do that, universal generalization. So consider any Z, and the next sentence after I say consider any Z would be, because I'm trying to prove this implication, now assume that Z is in B intersect C. Usually we merge those two sentences and just go ahead and say consider any Z in B intersect C. Now my goal is to prove that Z is in B. So this would be a good time to pause and think through how you would do it without necessarily knowing. Okay, I'm assuming you have maybe done that if you want to, and here's my approach. So the only way to possibly work with B intersect C is to use its definition. So we have to not be afraid to just use the original definitions of things. Otherwise we can get nowhere. So I have to unwind what is the statement Z in B intersect C. I have to unpack this. So I go back to the definition of intersection. B intersect C. Okay, let me rewrite this, but with the B and C symbols. So B intersect C is the set of things that are in B and in C, right? So then Z in B intersect C must be, according to axiom 5, must be the same as if I said this, but with the Z in place of the X. Z in B and Z in C. So let me go ahead and say that. Then Z in B and Z in C. So Z in B then, right? And that's it. I just needed to prove that Z is in B. So that's it for Theorem 30 Part 1. Theorem 30 Part 2, this one, is going to be really similar. Instead of proving subset B, prove subset C. So how about I just modify this one to prove that? So let's just say this is now Theorem 30 Part 2. This is now, we're proving subset C, and then I can carry it out basically the same way, except at the end, instead of noticing that Z is in B, I would notice that Z is in C. That's it. Okay, let's look at Part 3 here. Okay, there I've written it down. And let me keep this scratchwork area, clean this up. So what kind of thing am I proving? I'm proving an if-then statement. So I should assume the part in front of the if and then try to prove the part in front of the then. Assume that A is a subset of B and A is a subset of C. Now my goal is to prove that A is a subset of the intersection. So let me use my scratchwork area to break down what I have and what I want. So I have A is a subset of B. That means I have that everything that's in A is in B. And A is a subset of C. So I have everything that's in A is in C. And I want to prove that A is a subset of the intersection. So I want to prove that everything that's in A is in B intersect C. All right. So what I have is two universally quantified statements, and I want to prove a certain universally quantified statement. So I'll do a universal generalization type argument to try to prove this. And if along the way I want to use these, which I probably will, the way I will use them is universal instantiation. But don't let this distract you. We don't know yet, we don't know at this time what we're going to apply them to, right? So this, for example, tells us that everything that is in A is in B, but I don't know yet what thing in A I would apply this to. So I'm not going to let this distract me. I'm going to focus on my goal and then try to see if this comes in and helps out later on. So let's start the universal generalization for proving what we want, which is this. So consider any z, assume z is in A. Or let's do it all at once. Consider any z in A. And now my goal is to prove this. So I'm boxing it in so I remember this is my ultimate goal. If I prove this while keeping z arbitrary, then I will succeed and be done. Okay, so I've got an element of A. My goal is to show that it's in B intersect C. So actually, let me break down my goal further. By axiom 5, that's the same as proving z is in B and z is in C. Right? That's using axiom 5 and the definition of intersection. So this is my goal. In other words, I have two goals, this one and this one. Those are my two goals. So now I feel like I've unpacked what I have as much as possible, and maybe my only choice now is to use is to try to make use of these universals here. So let me remind myself what these say. This says if I have something in A, then I can conclude that that something is in B. This says if I have something in A, then I can conclude that that something is in C. Ah, well right now I do have something in A, Z. So I can apply these universals to this particular instance, to Z. So since Z is in A, and since every element of A is an element of B, remember this is just a short way of writing this whole thing. So I don't want to write this whole thing, so instead I just write it in the short way. Since Z is in A, and everything that is in A is also in B, Z is in B. Then you probably see what to do next. Since Z is in A and everything that's in A is in C, Z is in C. Okay, well I reached my goal, right? I needed to prove these two things and I've already proven them. So thus Z in A and Z in B. In other words, Z is in A intersect B. Let me make that extra curvy to make sure that it does not look like an and symbol. And that's what I needed, right? I needed to consider an arbitrary z in A and then prove that it's in B intersect C. B intersect C. What happened? Things got messed up somewhere here. Here. I think for some reason, I switched from B and C to A and B. So all I was trying to do was take this statement and rewrite it Z is in B, and this statement and rewrite it Z is in C. In other words, Z is in B intersect C. And that's actually what I needed. Take an arbitrary Z in A, prove that it's in B intersect C. So the next one is a similar kind of idea, but instead of intersection, it's union, and instead of maximality, it's minimality. And this one will be on your homework, but I just want to talk through how it describes the union as a special object among a class of objects. So you've got two sets, B and C, and you notice that the union has this property that it contains as a subset B, and it contains as a subset C. So let me draw a picture. Let's imagine that this blob here, everything inside the blob is the contents of B, and everything inside this blob is the contents of C. Then the union of B and C is going to be something that contains both B and C. So all the things inside B and all the things inside C are both contained in the union. Here's an example of something that contains both B and C. If I take this blob, which consists of everything inside here, that would contain everything that's in B and everything that's in C. So B would be a subset of the red blob, and C would be a subset of the red blob. But the red blob is quite big. We can go smaller. We can go to this green blob. That would also contain B and C and be smaller. It would be contained inside the red blob, so it's definitely smaller than the red blob, or at least as small, because it's a subset of the red blob. But we can go smaller. If you go to the smallest thing you can possibly go to, the tightest set that contains both, just barely hugging them, kind of including only the points that it needs to include, then that is the union. So that blue blob there is the union. So that's the idea of Theorem 31. It's saying B is a subset of the union. C is a subset of the union. And if you think about anything like A, which has this property that B and C are subset of it, then the union will be contained inside it, because the union is the smallest thing that contains B and C as subsets.